Hi, everyone, and welcome back to the Evidence Synthesis Conference in R. This session is Quantitative Synthesis in Network Meta-Analysis. And so to start us off, we're going to have Guido Schwarzer begin with a presentation. So take it away.
Okay, now you should see my screen. And okay, let's start. So this presentation is about our package netmeta for network meta-analysis. I would like to start with an example of 14 treatments for acute mania. And in total, there are 47 studies evaluating these 14 studies. Most of them were two-arm studies comparing 2 of these 14 treatments, but there were also 11 studies comparing 3 of these 14 treatments. Outcome here was a response to treatment, so a binary outcome. And here below, you see the graph for this network. And for the moment, let's just focus on one comparison. Aripiprazole here versus lithium. And as you can see here, there's just one study comparing these 2 treatments directly. But there are 6 studies comparing ARI with placebo and 3 studies comparing lithium with placebo. So the idea in a network meta-analysis is to use this indirect evidence in order to get a more precise estimate for this treatment comparison. And the same is true for all other treatments that you see here in this graph. So that's typically
it looks like the slides are not advancing.
What did you see? You couldn't see this. Oh, oops.
We were just stuck on the first slide. So.
Oh, great.
Sorry about that.
Then I will share my whole screen, and then let's do it like this. This is better?
Yes, that is working.
Okay, so I've been, for the last 2 minutes, I've been talking about this figure. You haven't seen that?
Yes, now we can. Thank you.
I pick up here is okay, or should I move on? So I say then again what I said here about this network. So we have this graph here, 14 treatments, 47 studies, a binary outcome here. We have just one study comparing aripiprazole with lithium, but there is lots of indirect evidence that we could use here in the network meta-analysis. And this is typically the primary aim that we have to combine direct and indirect evidence to get more precise treatment estimates. Other aim could be to rank treatments according to the efficacy. So the question would be, which of these 14 treatments should we use or prefer to treat acute mania? And assumptions that we have here are, first, that studies are independent. And the second assumption is that the underlying effects that we are interested to estimate, that they are consistent, and this means that for any difference of 2 treatments, we assume that the direct and indirect evidence that they do not differ. So the challenges that we have here are multi-arm studies, indirect comparisons, and the potential problem of inconsistency between direct and indirect evidence. And our package netmeta is one possibility to evaluate such data. We published it on CRAN about 7.5 years ago. It's based on this paper by Gerta, which is a frequentist method for network meta-analysis. And in a separate paper, we describe how we handle multi-arm studies, which is different to other approaches for network meta-analysis. So here, all pairwise comparisons for a multi-arm study are considered. And what we do here is we inflate standard errors for these pairwise comparisons in order to get appropriate weights in the analysis. And after this initial release, there have been several methodological extensions that we implemented, and I will talk about this in the coming slides. If you look at download statistics, you see that netmeta is among the most popular NMAR packages. And from these 3, netmeta is the only frequentist approach. So the other 2 are for Bayesian NMA. And over the last 8 years, netmeta has been used in over 100 journal publications. So in the next two slides, I will show you the core functions of the package. The first one is pairwise, which can be used to transform data sets such that you have the data that is needed for the functions which do the actual model fitting. And pairwise also calculates the pairwise comparisons. Then we have the functions to fit the NMA models. netmeta provides the standard NMA model, netmeta bin for rare binary data. And for component network meta-analysis, there is netcomp and discomp for connected or disconnected networks. Presentation of results, there's the netgraph function, forest function, netleak for leak tables. Regarding ranking of treatments, one can use netrank, which provides p-scores, which are a frequentist analog to sucra values. And if you have more than one outcome and would like to rank your treatments by them, then there is also the method of partial ordering of treatment rankings available in these functions here. To evaluate inconsistency, there is the net split function, which splits direct and indirect evidence, and then you can see whether they agree or disagree. NetHeatBot is available, and decomp design, which decomposes the Cochrane Q statistic by the designs of the studies. And for small study effects, there is the comparison adjusted funnel plot as proposed in this presentation. Here's example R code for this acute mania network. So we use here pairwise in order to calculate odds ratios and to transform the data set into the format that is needed by netmeta. Netmeta then does the actual model fitting. So here it's a random effects network meta-analysis. We specify placebo as the reference treatment. This is just for the presentation of results. And we also say that small values in the outcome are bad. So here the outcome were responses. We would like to see several responses. So small values are not good here in this case. And this information is used then in the ranking of the treatments. This command was used to generate the network graph that I've shown you. Here's the command for the forest plot, for the league table ranking, and so on. So you can see typically we just provide here the network meta-analysis object. I will not show you the results of the previous commands, but just this forest plot here, which has some additional information. So here we see the network estimates, which are combinations of direct and indirect evidence. And we always compare here the treatments with placebo. We also see here the number of studies that provide direct evidence. And we sort this forest plot here by decrease in p-score. So here at the top are the better treatments and the worse ones at the bottom. What you can clearly see here is that most treatments are superior to placebo regarding this response rate. So this is what you can do at the moment with netmeta. What's planned for the future? The first thing is that at the moment, only the decimal linear estimator is available for the between study heterogeneity variance. And we would like to also provide REML and ML estimates for that. And for that, we would like to link netmeta to the RMA MV function from Metaphor. The problem here is that Metaphor uses a different approach to handle multi-arm studies, and we have to find a solution for that. We already started, but are not ready yet. If we succeed here, then the next step would be to provide methods for network meta-regression, also using RMA MV and subgroup analysis. Then we would like to use resampling methods to describe uncertainty in treatment rankings. This contribution of studies Thodoros will talk about in the third talk in the session. And last, we also would like to provide a link to an R package for Bayesian network meta-analysis. So the idea would be to have an additional argument method, which then, if it's Bayesian, uses one of the available R packages for Bayesian network meta-analysis, and then one could use this new object and the other functions in netmeta for printing, plotting, and so on. That's it from my side. Thank you for your attention.
Thank you very much. That was a really interesting overview, and I'm excited to see explore the package on my own. So I appreciate that, and we'll take questions for this talk and all the talks at the end. So right now we're going to move on to our next speaker, David.
Thank you very much. So today I'm going to talk to you about a new package, Multi-NMA, which is for performing Bayesian network meta-analysis of individual and aggregate level data. So standard network meta-analysis and indirect comparison methods synthesize published aggregate data from each study under the assumption of constancy of relative effects. And what that means, for example, for an indirect comparison, is that the AB effect that we see in the AB study is exactly the same as we'd expect to see in the AC study if that study had included a B arm as well. And this assumption breaks down and we incur bias if there are differences in effect modifiers between studies. Those are variables that interact with treatment effects. Population adjustment methods aim to relax this assumption using available individual patient data, or IPD, to adjust for differences in effect modifiers between studies. Now, ideally, we'd have IPD from every study in the network, in which case the gold standard approach is an IPD network meta-regression. However, much more typically, we only have IPD from a subset of studies and then published aggregate data from the rest. The multi-level network meta-regression, or ML-NMR, is a recent extension of the NMA framework to synthesize mixtures of IPD and aggregate data in networks of any size whilst performing population adjustment. And it works, first of all, by defining an individual level regression model. This is, in fact, exactly the same model as we would fit in a full IPD network meta-regression if we had the data. And then we average or integrate this individual level model over each of the aggregate study populations to form the aggregate level model. And we do this using efficient and general numerical integration techniques. We actually use quasi-Monte Carlo integration here. And these methods are all implemented in the Multi-NMA package, which is a suite of tools for performing ML-NMR and standard network meta-analysis with individual patient data, aggregate data, or mixtures of both for a range of different outcome types. And the package includes functions that streamline the setup of these models, perform model fitting, and facilitate diagnostics. We can produce posterior summaries of quantities of interest, such as relative effects, treatment rankings, absolute predictions, etc. And we can create flexible graphical outputs, leveraging the power of ggplot and ggdist. Behind the scenes, models are estimated in a Bayesian framework using STAN, and the STAN models are pre-compiled by CRAN, which means that there's no user C++ toolchain or R tools required, which greatly simplifies things from a user perspective. So what does an NMA look like in this new package in Multi-NMA? Well, first of all, we start off with data in a long or tidy format. So one row per arm or contrast per aggregate study or per individual in the IPD. We then define the network. So we use these set functions to set each different data type, arm or contrast data, for example, or IPD. And then if we have more than one data type, we can combine these together using the combine. We then specify prior distributions and run the analysis using the NMA function. And we can fit fixed and random effects models. We can check for inconsistency using unrelated mean effects models. We can fit meta-regression and so on. Once we've fitted our model, we can then check convergence, assess model fit, and produce posterior results using the functions below. If we wish to fit a multi-level network meta-regression model, the only difference here is that we need to add in numerical integration points into the network. We do that using the add integration function. Everything else then is done the same way. So let's apply this to a quick example of treatments for plaque psoriasis. So we start off with some aggregate data here on one study with 4 arms. And you can see that we have some binomial outcomes, so event counts on each arm. And then we also have some covariates, some summary information, so means and standard deviations. And proportions for binary covariates. And then for the individual patient data, we have 1 row per individual. In each of the IPD studies, we have a binary outcome, and then we have their covariate information. Combining this all together into a network using the set functions to set each data source, and then combining them together using the combined network function. We tell it which columns contain the studies and the treatments, specify the outcomes, and we're also going to set a treatment class as well. And you can see then I can print the results of the network below. And for example, it tells you that it's connected, so we're all good. We can plot the network using the plot method. Here I'm choosing to weight the nodes by the total sample size and the edges by the number of studies making each comparison. And I'm also showing the treatment classes by coloring the treatment nodes too. Then to fit an MLNMR model, we need to add in some numerical integration points into the network. So we use this add integration function. And here, for example, I'm giving duration of psoriasis a gamma distribution with a mean and standard deviation taken from the aggregate summary data. And I'm fitting 1,000 numerical integration points for each covariate. And it's also using a correlation matrix automatically computed from the IPD studies. Onto model fitting, we use the NMA function, and here I'm fitting a fixed effects model with a probit link, and then I specify a regression model for the 5 covariates, their main effects and their interactions with treatment. And in this instance, I'm using normal priors on each of the model parameters. And once it's been away and fitted the model, we can then print the results, and you can see it's giving us a summary of the model that was fitted. So the regression model, it's automatically centered the covariates for us, and then it's giving us posterior summaries of each of the model parameters and convergence information as well. I can then plot the model parameters using the plot methods. Here I'm plotting the individual level treatment effects and the regression parameters. And then this is where the power of ggdist comes in. So I'm specifying here a half-I plot stat, which means that we get these sort of densities here in the plot, as well as the points and the credible intervals. I can produce population average relative effects using the relative effects function. And here I'm specifying a new study population for which to produce these population average relative effects using the new data argument. If I omit this, then I end up producing these population average effects for every study in the network. But here I'm specifying a new target population to produce these estimates for. And then you can see below that we can plot these again using the plot method. Very similarly for population average predictive probabilities, using the predict method now. And the only difference here now is that I'm specifying a distribution for the baseline probit probability of response. And then once again, we can plot this using the plot method. And there's much more that we can do. So we can produce rank probabilities. Here I'm showing you some cumulative rank probabilities. We can check model fit, so DIC, residual deviance. We can produce residual deviance plots, compare residual deviance contributions between different models. So I've really only scratched the surface here today. If you'd like to find out more, you can visit the package website, which includes illustrated documentation and detailed walkthroughs of lots of example analyses. If you'd like to find out more about multi-level network meta-regression, you can read our paper, which was recently published in JRSSA last year. And if you'd like to contribute in any way, please get in touch on GitHub. Thank you very much.
Thank you very much. It's exciting to hear this presentation. I actually had never heard of a multi-level network meta-regression combined with IPD. So thank you. And we're going to move on to our next speaker, Thodoros.
We can't hear you.
Yeah, can you hear me?
Now we can.
Okay. Yeah, okay. So I will be talking about how to estimate the contribution of each study in network meta-analysis. Okay, I will start with the contribution of studies in pairwise meta-analysis, where we compare two treatments, say treatment A versus treatment B. We do that by synthesizing various studies, examining this comparison. Each study represented here with dotted lines is weighted by the inverse of its variance. and the summary effect is theta hat. So the contribution of each study is its weight normalized by the sum of the weights, and the weights sum up to 1. Okay, so in network meta-analysis, we can compare more than 2 treatments, not only A versus B. This means that not only we can borrow strength from indirect comparisons, but we can compare all pairs of treatments, even those that have not only been directly studied, such as C versus B here. So network meta-analysis can be performed as a 2-stage process. And in the first stage, we do a normal pairwise meta-analysis. And in the second stage, we synthesize the pairwise effects to get the theta superscript and network estimate. So this is done through the H matrix. And this H matrix is calculated exclusively by the variances, and it resembles the hat matrix of linear regression model. Each row of the H matrix refers to a single network effect, so it's row, and each column to the respective direct effect. So for the A versus B comparison, we're interested in the first row here. So the contribution of studies having directly compared A versus B, which is also called direct contribution, is by definition equal to the respective element of the H matrix, which is here with bold font. And this means that the solution is of simply normalizing H elements is excluded, given that also the sum of the H row elements is not 1 in general. So what our approach was motivated by the observation of Koenig et al. That the hat matrix row elements represent flow from A to B in the respective flow graph, as you can see here, and the total flow is always 1. So assigning contributions becomes the task of partitioning or decomposing the flow of the aforementioned flow. Okay, so in order to do the flow decomposition, we break up the flow into a number of streams of constant flow, where the contribution of each stream is equal to its flow. The stream is therefore defined by its path and its flow. For example, in this figure, we have 2 streams, the upper one and the lower one, the blue and the orange. In order to calculate the contribution of a comparison now, not the stream, we first break up the contribution of each stream into its constituent comparisons. And then we assign the contribution by dividing by the stream's length. So this is the flow A CDB divided by 3. So for comparisons that are included in multiple streams, as in here, we have to add the individual comparison contributions in order to get the total contribution of the comparison. And finally, we get the study contributions by the use of pairwise meta-analysis weights. So we use the weights of the aforementioned pairwise meta-analysis. Okay, so through the collaboration with the Institute of Medical Biometry and Statistics of University of Freiburg, the contribution matrix will be included in the upcoming version of netmeta. And this will be as simple as calling the netcontrib function to the netmeta object. And we will get the contribution matrix like that, where each row is refers to a network estimate, and the column to a direct estimate, a direct comparison. So I would also like to introduce the NMAdB grant package, which gives access to the database of network meta-analysis curated by ISPM Bern, Switzerland, and University of Ioannina, Greece. And through NMAdB, we're able to access 213 published networks, a number which is expected to rise since the database is being currently updated. So the graph is an application of the contribution matrix to the database. And we see here the distribution of contribution of streams by their length. And what we see is that the direct contribution is only about a third, 30-something%, while the contribution of a stream of length 2 is significantly more per average. And what we see, so wanting to give a real-life use of the contribution matrix now, we present the judgment of the influence of study risk of bias as is performed in Cinema, the web application we developed for judging the results of network meta-analysis, which is available in this link. In this example, we can see a series of bar charts, each one referring to a different network estimate. Each block refers to a study, and the size of the block is its contribution, and the color, its risk of bias. And as you can see, although for each comparison, the exact same studies are included, the distribution of risk of bias differs substantially. So that's all. Thank you for listening.
Thank you very much, Thodoros. And now we're going to move on to our next presenter, Hugo.
Hello. So you should be able to see my screen now. Is that working?
Yes.
Just a moment. Let's actually get me on the slides. There we go. Right. So I'm going to be talking now about MBNMAdose, which is an R package for incorporating dose response information into network meta-analysis using the model-based network meta-analysis framework. That's what the MBNMA stands for. So I'm going to talk a little bit about how to deal with different doses in standard NMA and why they can be a bit of an issue and sort of lead to some sort of decisions that have to be made about how to deal with that. And then talk about how we can, one sort of approach we can use by modeling the functional dose response relationship using the MBNMAdose package. And I'll talk a little bit about some advantages of this and also the kind of key assumption behind this before finally going on to talk a little bit about other features of the package and some future developments which we're hoping to build in. So firstly, when you've got a network meta-analysis and you have multiple doses, there's kind of two approaches for dealing with them. And one is to lump those different doses together. So that's sort of as we would show on the network plot on the left, where we kind of assume that different doses have some sort of similar or common effect within a particular agent or drug. And we know that while that sort of might allow us to sort of do the analysis more easily, that's likely to introduce heterogeneity or inconsistency, because we know that biologically different doses of a drug are very likely to have a different effect. That's sort of the point of giving different doses. So that's not really a great solution. The other approach is to split all of your different doses, which means that you assume that there's no relationship between different doses of the same agent and they're totally independent. And if we do that, we're not really using all of the information we have, because there is some information between different doses that we should be able to sort of glean. And we also can end up with very sparsely connected networks, very imprecise treatment effects, and in some cases also disconnected doses that we won't be able to estimate relative effects for using standard NMA. So another approach, rather than to choose one of these sort of not ideal methods is to model the dose-response relationship functionally, and we can do that using MBNMAdose. So what I've got here is a sort of plot of sort of function structure on the right, but we start by running the MBNMA network function just to create a network object, and then we can kind of investigate that. We can plot the network plot either at the dose level or at the class level, run some other sort of preliminary investigations. And one of the ones we also might want to look at is just to run a simple standard network meta-analysis and plot the different relative effects at each dose of every agent in the network, because this allows us to get some idea for what sort of dose-response relationship there might be, whether there is a sort of one to worry about, and also what shape it might take and what function we might want to try to model. So here we've got one agent, allogliptin, and we can see that there's very clearly some sort of dose response, and it's nonlinear. So we want to try to model that in some way. And that's where the actual MBNMA model fitting comes in. We do this, this is done using a Bayesian framework in JAGS, sort of behind the scenes. And for the modeling framework, we define a treatment as being a specific dose of a specific agent. And we can then apply a function to this, a dose response function, to any treatment in the network. And we can choose a particular dose response function that we think might fit our data well, and also that we think is sort of biologically or pharmacologically plausible. So one that we found works for most of the data sets that we've looked at is the Emax function, which is used a lot in pharmacometrics. And this has two parameters and creates a sort of nice nonlinear relationship, which looks very similar to the allogliptin relative effects in the slide that I showed you before. And the way we apply these functional forms is that we apply them onto the relative effects within studies. So we don't have to worry about modeling prognostic variables or anything like that. And then from our model, we can get sort of useful things like rankings for each of the agents and forest plots. But one of the really useful outputs is to look at predictions from the model. And we can easily output these in the package and plot the dose response curves for each agent that we are predicting. And then on top of those, we can also add an option to plot the split network, the split NMA predictions. And these are the little vertical lines representing the split NMA and the credible intervals. And what we can see here is that generally our predictions are in line with what we'd expect from a split NMA. So that's a good validation of the model. We can use these predictions as kind of a method for validating the robustness of our sort of dose response assumption. And we can also see that there's a little bit more precision. We have tighter credible intervals from our dose response model. And that's because we're using additional information there. We're kind of gleaning a little bit more from the dose response function. So this gives us more precision over standard NMA, but it comes at the cost of making an additional assumption regarding the dose response relationship. And if this assumption doesn't hold, then it will introduce bias into the estimates. But we can easily evaluate that because we can look at our data and compare, does this fit well with our data? So that assumption can be evaluated within the ranges of doses for which we have data available. Another sort of function of the package that we've been looking at recently, and we've just published a paper on, is that it can be used for linking disconnected networks, which can be a real problem in health technology appraisals. So these are just sort of two example networks here. And let's say we wanted to compare the treatments in each network indicated by the dotted red line. Well, we can't make that comparison using standard NMA approaches because there isn't a pathway of head-to-head evidence connecting the treatments. But because of the different doses within this data set, we can actually model the dose response functions using MBNMAdose, and that then allows us to estimate the relative effect between the treatments that we're interested in, or between any other points on these dose response curves. And we've, in the paper that we've just published, in some quite limited examples so far, we'd like to do a fuller simulation study, but we found that this produces pretty robust estimates, provided the dose response relationship is correctly characterized. So some other features that are in the package, we can apply class effects to parameters in the model. So if we have some reason to believe perhaps that for certain parameters, perhaps the Emax in the Emax model is shared within a class of agents, then we can model that, and we can do that sort of based on pharmacometric properties that we believe might be plausible. We can also do consistency checking, which is really important in network meta-analysis, either globally or locally while accounting for the dose response. And we can also model specific dose response functions for specific agents if we believe that they may be different in the network, or if we're dealing with some really different classes of agents. What I'm hoping to do in the future is to combine this with another package that we have that's available on CRAN called MBNMA time, to produce models that can account for both time course and dose response simultaneously, because this would be a really nice way of sort of wrapping up this framework and bringing it all together. But the time course models can take a while to run because there's correlation between time points, so we have to fit a multivariate likelihood. So an implementation in Stan would also be something that I'd quite like to work on. So yeah, these are the two sort of key methodological papers behind the package. Thanks very much.
Thank you very much, Hugo. That was really interesting to hear about. And now we are going to have our last presenter, Mike.
Hi, today I'll be talking about this package, BNMA, which is shorthand for Bayesian Network Meta-Analysis using JAGS. My name is Michael Saw. I have been working on this project with Professor Chris Schmid from Brown, and I'm currently a PhD student in University of Bern, Switzerland. Recently, there has been many packages of Bayesian NMA in R, including GMTC, BNMAdose, BoxNet, BNMA, and Multi-NMA. The goal of this presentation is not to compare different packages, but to go over the package we have developed. BNMA implements models described in nice document. This document provides detailed description of the Bayesian NMA model. BNMA can model normal, binomial, and multinomial outcomes. Required input includes outcome, study indicator, treatment indicator, and total number of observations or standard error. Based on the specified input, BNMA creates JAGS code and initial values and automatically runs Bayesian NMA model. We will demonstrate this package using the smoking cessation dataset. This consists of 24 studies, including comparing 4 smoking cessation counseling programs. This is the first 5 studies of the smoking dataset. And we will briefly go over the Bayesian NMA model. Since our dataset is binomial, we fit a binomial model. And I refers to the trial, K refers to the arm. The link function is eta I plus delta I1K. Eta I are the trial-specific baselines, and delta I1K are the trial-specific treatment effects. For a random effect, we can model the delta I1K with a normal distribution with average treatment effect D and heterogeneity parameter sigma squared. NMA requires consistency equations to hold, and equal variances are commonly assumed. So this model can be fitted using BNMA package as follows. We first set up the model using a function called network.data, and we specify the input, response, and type. Then we can run the model using a function network.run. Then we can summarize the result using the summary function, and this is the summary we get. So the odds ratio for treatment 4, the group counseling, is 3.01. So the model estimates a 200% increase in the odds of quitting smoking for group counseling compared to no intervention. There are some pre-built summary visualization functions, and this is force plot. Additional details that we have includes checking convergence. So even if the user didn't specify the initial values, we generate the dispersed initial values, and then we use the Gelman-Rubin diagnostics to test convergence of parameters such as the eta I, the baseline risk, the average treatment effect, D, and the heterogeneity. We check convergence every set size iteration, and once the samples are converged, it keeps the last half of the converged sequence. If the user requires more sample size, we can specify through the parameter called n.1. So that was a basic NMA model. We have extended this basic model to, for instance, have a different assumption on baseline risk. Instead of having baseline risk to be independent, we can assume it to be exchangeable. And so we modeled the baseline risk using a normal distribution with a common mean and between study variance, E and sigma E squared. That this extra assumption of random intercept should lead to a greater precision. However, this comes at the price of using the between study information, meaning the treatment effects are no longer estimated only by the usual differences within studies, but also by the differences between studies. We can fit this model using by adding a parameter baseline risk and setting it to equal exchangeable. This is the summary result for fitting this model. Now the common mean for the baseline risk is estimated to be minus 2.4912, which is equivalent to a baseline probability of quitting of 0.076. So another model that we have added is we can use baseline risk as a meta-regression, similar to how we include the covariate information. So by adding this baseline risk as meta-regression, we can explain possible source of heterogeneity. There are 3 different assumptions we can make. There's common, exchangeable, and independent. And if the user wants to assume a common effect, treatment and covariate interaction, then the user can just simply add this parameter baseline equal to and set it equal to common, and it will fit this model. So this is the summary of the result. And now we have a new parameter BBL, which is the regressor for the baseline risk regression coefficient. So now the interpretation for the odds ratio, which is 3.17, is now the treatment effects of the group counseling for patients with a baseline probability of quitting of 0.06. To summarize, we quickly showed how to fit simple Bayesian NMA using smoking dataset with the BNMA package. We demonstrated how to incorporate baseline risk via a exchangeable assumption or a meta-regression. And the following slide is uploaded in my private website, mikejseo.github.io. And here are the references. Thank you.
Thank you very much, Mike. That was really interesting. And thank you to all the presenters for sharing your work. I'm really excited that now we have a little bit of time to talk about each of the presentations. So I don't see questions in the channel yet, so I'm just going to jump in with one that I had actually. I've dabbled in network meta-analysis, but understand less of the technical details. And so I was kind of wondering, Hugo, in your presentation, talking about this idea of linking disconnected networks, I was kind of wondering what the group thought about as a whole, kind of this idea of, how can you do that in a way that doesn't violate the assumptions of transitivity? Are there safeguards, and is that, a viable option for lots of kinds of research studies, or is there only a certain kind of research that would be, you could link disconnected networks in a network meta-analysis? So question for you, but then also I think for others in the group to jump in as well in terms of thinking about transitivity and consistency.
Yeah, so I think one of the the issues to do with linking up networks is if you're really focusing on modeling the relative effects, then if you're not so concerned about modeling the relative effects, then kind of the network doesn't need to link up. But then you need to be able to adjust for all of the prognostic factors, and plenty of those won't necessarily be reported in studies, some that might be really important and might confound your effects. So there are sort of, trying to sort of link up networks without sort of violating some of those assumptions is really tricky. And there are a few sort of good methods for doing that. I have actually seen in the netmeta package as well. I think it implements the component NMA approach, which is another sort of, similarly to sort of modeling the dose response, another way of kind of using your treatments, sort of information about your treatments to connect up, to make those links. I'm not sure what Guido, and as well, I know that David, because of the adjustment in multi-NMA, probably has some thoughts on that.
So in netmeta, you can use the discom function if you have a disconnected network. And concerning the assumptions of transitivity, I mean, what you can do there, you can add interactions and to relax these transitivity assumptions. That's pretty what I can say on this.
I'm happy to come in and say a little bit as well. I think Hugo's really covered it there. In that I think the least assumptions you can make is some form of dose response assumption. I think that's really nice. And Hugo's done some work on connecting networks via dose response. And then kind of Guido's component NMA. That's also you're not throwing away any randomization with either of these methods. You're still synthesizing relative effects. There have been some population adjustment approaches where essentially you try and either impute a baseline response for the single arm studies or disconnected studies. You're kind of trying to predict absolute effects and absolute outcomes then, and that's really hard to do. If that was easy, we wouldn't do randomized controlled trials. We just regress and adjust for everything, but that's not how life is. So certainly using these sorts of regression adjustments to try and connect disconnected networks is a very strong assumption, and I think should really be an absolute last resort. I think the component NMA and the dose response NMA are much more reasonable. But yeah, this is kind of very much ongoing research.
The problem is you need the data to be able to do that. To be able to do a dose response sort of function, you need to have information at different doses, and the same with component NMA. You need to have these combinations to be able to sort of model those interactions, I guess, without all the assumptions. And that's not always provided in data sets that you want. I think from the perspective of dose response, a lot of that evidence is there in sort of phase 2 trials, but they're often not included in the kind of data sets and sort of health technology appraisal submissions that we see, which is a real problem.
Yeah, and along those lines, I think I was wondering, in terms of the size of the, the sample of studies that you would need, what kinds of numbers are we talking about? And is that going to be feasible for someone, who's taking on an NMA that also wants to look at these issues?
In terms of the dose response stuff, you really don't need a huge data set. It's more about how many doses there are available for each drug or each agent that you're modeling. Because if you don't have, if you only have 2 doses, or if you only have a sort of placebo dose 0 and a higher dose, then you'll only be able to fit a dose response function with one parameter without making some sort of other assumptions. I guess the nice thing about dose response relationship is also that those are typically based on some sort of kind of receptor binding properties. So you can perhaps get some of that information as well and use that to inform priors, which will sort of give you a bit more information. But in general, if you have a study that has multiple doses, that's more valuable than sort of several studies that are just sort of 2-arm trials that compare different agents at just a single dose. And that's why those sort of early phase trials, those dose finding trials, are really helpful for that.
Thank you. That's really helpful. I have a question for Mike from Wolfgang. The question is, I'm curious how you would go about choosing between different models in your approach.
I guess I think one thing that comes into my mind is when you want to choose between maybe random effects or fixed effects. A lot of times I think you look at the DIC, but I guess this one, like I've talked about the baseline risk, and I think it's not really about the model fit, but whether the assumption that you're making is valid. So if the baselines are, in fact, you suspect them to be different, then maybe you should fit a model that has that adjusts for baseline risk. But I think it's quite exploratory and subjective. So you should try fitting different models and see what kind of results that you get. And yeah, but that's just my thought. Thanks.
Thanks, Mike. Yeah, so I'm giving people a chance to ask some additional questions, but in the meantime, I didn't know if any of you had questions for each other based on, your work in different areas of network meta-analysis. I think that would be really valuable if you all had anything you wanted to ask of each other.
I have a question for Thodoros. Thanks for your talk. It was really interesting. I was wondering about whether you can derive these contribution matrices for Bayesian NMA, or is it only for frequentist approaches at the moment?
Yeah, so far it's just for the frequentist method. The problem is how to derive the prior contribution, the contribution of the priors. And yeah, that's a problem. Because you have the effects, and let's say you somehow back calculate an H matrix, but I'm not sure that this is going to be unique for a class of priors. Yeah. So that's a problem. Yeah.
That's just we've done some work on kind of a related problem to do with threshold analysis, so changing the data and kind of working out algebraically how that would change your posterior in a Bayesian setting under some essentially normality assumptions. If you assume that everything's normal, then you have conjugacy, and you can kind of pull things through that way. And I think there is an overlap there, because that relies on essentially an influence matrix as well. And so I think perhaps there is some way that you could extend your ideas to Bayesian methods, probably in a similar way, perhaps under some assumptions.
Okay, nice. I will have a look at the influence matrix.
Great. Well, thank you all for participating. It's been really fun and interesting. And if there are no further questions, which I don't see anywhere, I think we'll end a few minutes early. So thanks again.